Complex can be complicated. There's an underlying structure very often, but it is far from simple. Now, when we say underlying structure, we mean a topology, where topology is a way in which constituent parts are interrelated or arranged. It's the general shape, the underlying structure. In big data, underlying structure often has high variety. We see lots of different features at all different scales, lots of different varieties of these structures underneath. Because of that, every application with big data tends to be unique. What works well in one application may not work at all in another, even if the data sets are the same or very similar. Now, how do we work with big data? First, we want to understand the process from which data is sampled. Data is just a tool for understanding the process. We want valid conclusions that remain true even if another data set were to be sampled from that process. For example, user preferences is about users, not about data. There are two issues in regards to this we must continuously address. Bias, the degree to which sample averages converge to something other than expectations, and overfitting, the degree to which the results are only true for a data set, not of the process which produced it, and therefore not true of another data set collected from that process. So we're working with unique big data. We have to explore, get to know our data, get to know its own unique character. Preprocessing by imputing missing values, changing the representation of the data, predictive models via machine learning algorithms, and then we assess the results. And we repeat this process over and over. Pre-processing becomes feature selection, feature engineering. We want to understand the topology and how it implies the theoretical expectations. That is, we want to understand how the process is represented by the data. And after that, we can make predictions, draw conclusions, and so on. For now, we're just going to assume data is in the form of a rectangle. Features as the columns, observations as the rows. But these ideas apply to all forms of data. There are many methods for pre-processing, but be careful. Pre-processing always causes bias. Use with caution. Now what about imputing missing values? We impute, and that always creates bias. In fact, if there's only a very few missing values, it might be best just to drop all the observations that have missing data. However, it's usually better to impute, where imputing is an educated guess based on other characteristics and properties of the data. For example, the grades data. We replace missing exam scores with exam averages. Is that better? Should we maybe have replaced based on a pass-fail status? Then we're ready for transformations with no loss of information, standardization, scale to a mean of 0 and a variance of 1, rescaling, scaling to a given range, and then one hot encoding. Let's explain with an example. So suppose we have east, north, west, and south. If we let east be 1, north be 2, west be 3, and s be 4, that's obviously biased. For some reason, s has a bigger value than e. So instead, we use combinations of 1s and 0s. So east would be 1 and then 3 zeros, north would be 0, 1, 0, 0, west would be 0, 0, 1, 0, and s would be 3 zeros and a 1. Thresholding, which causes loss of information, means we map to extremes. So let's look at an example. We're going to use matplotlib and explicit imports. We're looking at our favorite die example here. Notice we have observations and trials and the preferences. Notice that we're going to use the targets as the preferences and drop the observation. So notice the data is now just the trial data. And a histogram of the trial data shows that it's mostly 1 through 6s. They are in common to the two die. They're from 1 to 0 to 7. And once we standardize using scale, notice they're now centered at 0, a mean of 0, and a standard deviation of 1. Now, let's look at a different example. This is what's called Olivetti faces. 400 grayscale images divided into 10 images of 40 people. So this is a little helper function we define. We fetch the faces. Notice our targets. There's 10 images for each of 40 people. Here are the 40 people. So it's preparing, and there you see the 40 individuals, the subjects, and each of those has 10 images. For instance, here are the 10 images for the first subject. Now, we can actually use this as data. We can calculate, for instance, an average face. So there's the average over the entire data set. But this is average is more of a measure of fact. The eyes and other features have been aligned already. So the eyes and the nose and the mouth, they're all on the same level in the same place in the picture. So if we subtract the face, you don't get the face removed. And that's because facial features are spread out over many pixels, many regions. And so all of these standard scalars, we end up pretty much with just essentially the same pictures we started with. So when we say pre-processing, we don't mean necessarily that we're removing things. It's better to think of it as balancing. So for instance, the grades data, each exam's equally important in some sense, but the average exam scores change from exam to exam. So we don't necessarily know what each exam is telling us. That's what we want to fix. We want to have all the exams on the same footing. So here's the data. We can look at some histograms. And notice we're going to split this into two groups, those who pass and those who fail. That's the groups we want to compare. We're just going to look at the first 4 exams. The 5th exam is actually the final exam, so can't really rescue them at that point. So here are the exams. The top is the zeros and the bottom is the ones, and you'll notice that we really can't tell exactly how to infer anything from the relationship of these two. But let's suppose that we actually standardize the data. So remember that our problem here is that the means change from one exam to the next. So for example, the points are different. The exam scores are different each time. So if we look at the standard data, you'll notice that we now can produce histograms, and these histograms have the property. So now we can compare the exams because they all have the same mean. Notice all the things that are below average in exam 2 for those who fail, and yet in exam 2 for those who pass, most of the scores are above 0. So it gives us a basis for comparison. Exam 2 is in some sense the turning point. So we can actually use exam 2 and exam 3. So exam 2 is the turning point. We can actually use exam 2 and exam 3, but notice in exam 2 that we really have this separation between those who pass and those who fail. And that's because we know the average now is at 0. So more methods for pre-processing. We have dimensionality reduction. It uses linear algebra based on singular value decomposition. And typically You do this when you have more information than necessary. For instance, if you're looking at images of faces, then you might want to reduce just to the essential information. And also there's manifold learning, which we'll talk about later. And this is where we try to figure out what the underlying structure is. There are many others also, some of which we'll introduce later. We'll always use these with caution. So let's look at basic feature engineering, principal components analysis. What we're going to assume is that we have some data on the line 4/3 x plus 3. And that corresponds to a cosine of theta is 4/5 and a sine of theta is 3/5 in this line with the x-axis. So we're going to do this first centering the data. Once we observe that feature engineering often solves the problem before we even get to the algorithm. So there are the means. Let's look at the what happens when we subtract the means. Notice we've centered this data now at 0, 0. And a slope of 3/4 corresponds to a unit vector of 4/5, 3/5, 0.8, 0.6. And there's our actual slope vector. And notice it's right along the line of slope 3/4. Now, principal components analysis does exactly the same thing. So we import the PCA command. This creates an object, and the PCA object is then fit to the data. And we can then assess the results using the explained variance. But it may be easier to look at the explained variance in terms of a ratio, because we now see that more than 99% of the variance is explained by the first component. So what is this component? Well, notice there's very close to 0.8 and very close to 0.6. So this is actually the slope vector. We can get the averages. That's very close to what we calculated above. And if we then look at what we get from the PCA in terms of the mean and the first component, it's right there, right along the line itself. And we can actually transform the data and notice that it simply rotates the data so that it's all on the x-axis. So it's the same data we saw originally, but now, except for some noise, we can use just a one-dimensional representation rather than a two-dimensional representation. So let's say what happens if we do the same thing with the faces. So we're going to use randomized PCA and also whitening. So we'll first make everything maximally uncorrelated. We get a randomized PCA estimator, and this is just a probabilistic version of PCA. It's just faster when you have large data sets like images. So let's plot what a few of those look like. So there's the first few components. Now these components are not actual faces. They're just like the vectors that we saw above. What we really want to look at are the variance ratios. And let's do this with a cumulative sum. So these are the first 10 explained variance ratios. Let's look at a cumulative sum. Let's see how long it takes to explain the 95% of the variance. So we do the cumulative. Now we have a plot, and you'll notice it crosses somewhere about the 120 to 130 range. So 95% of the variance explained after about 120 components. And exactly it's 122. So the variance is explained after 122. Now let me just point out sparse data. If the data is mostly zeros, we only store non-zero values and where they occur. This allows us to work with incredibly large data sets. Now, if we use standardization, the sparse data may become dense, which means not sparse. But this is actually something you can fix because all the zeros will be mapped to another specific value. So instead of storing only non-zero values, we store values that are not the same as what the zero is mapped to. Notice that one hot encoding also produces sparse features. So preprocessing may actually be the most important component of a machine learning application. It's often called feature engineering these days. It also includes feature selection. We'll talk about that a little bit in the next video. But preprocessing can introduce bias. It's possible that a subsequent algorithm only learns the bias you created in the preprocessing. So bias is a huge issue, something we have to be careful of. Always preprocessing we use with caution.